All right, we are continuing chapter 12. This is section 2. We're going to talk about Newton's first and second laws of motion. So before we can really get started, we need to talk about a few very important, influential people that gave us or helped to get us to Newton's laws of motion. And the first is Aristotle. He lived from 384 BC until 322 BC. He used observation and logical reasoning in his deductions from motion. And his idea of force and motion was that a force is required to keep an object moving at a constant speed. The second person that was very influential is Galileo Galilei. He lived from 1564 to 1642. And he was more of the type to use experiments. He liked to be kinesthetic and hands-on. And his idea was that moving objects are not subjected to friction or any other force, and that those objects would continue on indefinitely, forever. So nothing can stop an object. It will keep going. Now, do we know that to be true? No. We know if we take a ball and we roll it down the hallway, it will slow down and stop. Or if we roll it hard enough, it's going to stop once it hits a wall or the door at the end of the hallway. So here we come to Newton. He was born in 1642, same year that Galileo passed away, and he lived until 1727. And in 1665, Newton built on the framework of Galileo and Aristotle. So he took what they had already been focusing on and expanded on those topics. So he actually wrote what is known as the Principia. That's one of his books, and I actually have a copy of it in the classroom if you guys would like to look at that later. But this is Sir Isaac Newton. So now that we've seen who the influential people are, let's look at what the laws are for motion. The first law states that the state of motion of an object does not change as long as the net force acting on the object is zero. Now that seems a little confusing. Let me clarify. An object that's at rest will stay at rest, and an object in motion will stay in motion. That's Newton's first law. It's also known as the law of inertia, which states that the tendency of an object to resist a change in its motion. So for example, if something is moving, it wants to stay moving. If you are in bed asleep in the morning, you want to stay asleep. You don't want to have to get up and come to school, right? That's inertia. Newton's second law deals with force and acceleration. So it states that the force of an object depends on the acceleration that it has and the mass that it has. So we can write that as a formula. Acceleration equals force divided by mass. Now we've looked at formulas already, and we'll manipulate this later in class. But acceleration, A equals F over m. Now this is written a little bit differently in your reference packet, and we'll go over that, like I said, in class when we review the manipulation of this formula. So it depends on acceleration and mass. That's very important for you to remember. So here's our example. An automobile with a mass of 1,000 kilograms accelerates when the traffic light turns green. If the net force on the car is 4,000 newtons, what is the car's acceleration? Well, here's our formula. Acceleration equals force divided by mass. We have 4,000. That's our force. So the net force on the car is 4,000 newtons. And then a mass of 1,000 kilograms. So force in the numerator, mass in the denominator, 4,000 divided by 1,000. You should get 4. And we're solving for acceleration here. So remember, from Chapter 11, acceleration is in meters per second squared. So you'll include that with your units. Let's take a look at a practice problem. A boy pushes a cart of groceries forward with a total mass of 40 kilograms. What is the acceleration of the cart if the net force is 60 newtons? So same type of problem, same situation here. We have force in the top, force in the numerator, so we have 60 newtons. And then we have 40 kilograms in the denominator. So 60 divided by 40 should be your number. So if you'll go ahead and plug in 60 divided by 40, we'll go over the answer tomorrow in class. More practice, and this one's on your own. We'll go over how to do this one tomorrow. What is the upward acceleration of a helicopter with a mass of 5,000 kilograms if a force of 10,000 newtons acts on it in an upward direction? Go ahead, plug that in, solve that in your notes. Make sure you have that in there. A couple more terms, and then we'll be done for today. Weight is a very important term. We're talking about force here. So your weight on Earth is actually the force of gravity acting on you. And how we figure weight is we take the mass of something and we multiply it by the acceleration due to gravity. So W equals mg. Now remember, from chapter 11, 9.8 meters per second squared is the acceleration due to gravity. So we are going to plug that in to our formula, and you should only have one missing piece. So what's the difference between weight and mass? Well, weight is a measure of the force of gravity. It's in newtons. Mass is the measure of the inertia of an object. It's in kilograms. Your mass, no matter where you are on Earth or where you go in this universe, your mass is going to stay the same. However, your weight will change based on where you are located. The closer you are to the center of the Earth, the more your weight will be. The farther away from the center of Earth, the less your weight will be. Now on the moon, for example, the moon has a force of gravity that's about 1.61. It's about 1/6 of that here on Earth. So your weight on the moon would be less. Mass is still the same, but your weight would be less. And that's it for today.